Have you ever looked up at the night sky, like actually stopped what you were doing and just looked up, and wondered if the stars you were seeing might not really be there anymore? I did that a few weeks ago. It was maybe 1 a.m. I was walking back from a late shift, crossing the Manhattan Bridge on foot because the subway felt suffocating that night. And I stopped in the middle of the bridge. You can actually see a handful of stars from there if the sky is clear enough, and the light pollution dips for a second. And I just stood there, staring up. And then this thought hit me. This thought I couldn't shake for days afterward. What if those stars are already gone? Not like, what if they burned out recently? I mean, what if those lights I'm looking at left those stars thousands of years ago, traveled across the universe for longer than human civilization has existed, and what I'm seeing right now is just a memory, an old photograph that's still arriving? And this is where it really starts to get uncomfortable. What if that's not even the most disturbing part? What if most of the universe still looks visible to us, but has already become forever unreachable? Not because anything blew up, not because something catastrophic happened, but simply because the universe itself, the space between everything, is stretching apart faster than we could ever possibly cross it, and has been for billions of years, quietly, without asking our permission. We look out at this vast, glittering cosmos and we think, it's all out there, waiting, and someday, somehow, maybe we'll reach it. But what if that's wrong? What if the vast majority of what we can see right now, we could never actually get to? Not if we started today, not if we started 1 billion years ago, not ever. That thought made me stop walking. Actually stop. On the bridge, in the cold, at 1 a.m. Because here's what really messed with me. The universe isn't hiding this from us. The light is still coming. The galaxies are still visible. Everything looks fine. But the truth buried inside the physics, inside the math that describes how space itself behaves, is that most of what we see may already be permanently, cosmically, forever beyond our reach. And scientists still don't fully understand why. That's what this video is about. Sit with me for the next couple of hours, because by the end of this, the night sky is never going to look the same to you. I promise you that. When you look at the night sky, you are not seeing the universe as it is right now. You are seeing it as it was. This is not a metaphor. This is not poetry. This is just physics. Light travels fast, 300,000 kilometers per second. That's about 186,000 miles per second. It's the fastest anything in the universe can move, and it still takes time to get from one place to another. Here's a small-scale example first, just to make this real. The moon is about 384,000 kilometers away. So, the light bouncing off the moon takes about 1.3 seconds to reach your eyes. When you look at the moon tonight, you're seeing it as it was 1.3 seconds ago. That's not scary, that's fine. But let's go bigger. The sun, the light reaching your eyes right now, left the sun about 8 minutes ago. If the sun suddenly just stopped existing right now, vanished completely, you wouldn't know for 8 minutes. You'd be sitting there, drinking your coffee, totally unaware that the center of your solar system had just disappeared. Okay, still kind of manageable, but here's where it starts to feel different. The nearest star to us, not counting the sun, is Proxima Centauri, about 4.2 light years away. The light you see from Proxima Centauri left that star 4.2 years ago. It's been traveling through the void of space for over 4 years before hitting your retina. Now, push further. The Andromeda Galaxy, the nearest large galaxy to us, the one you can actually see with your naked eye on a very dark night, is about 2.5 million light years away. That means when you look at Andromeda, you are seeing it as it was 2.5 million years ago. 2.5 million years ago, our earliest human ancestors were just figuring out how to chip rocks into crude tools. Homo sapiens didn't even exist yet, and the light that tells us what Andromeda looks like today left that galaxy before any of that happened. Let that sit for a second. We don't see Andromeda as it is. We see it as it was when humanity's ancestors were just getting started. Now go further still. The most distant galaxies we've ever observed, things spotted by the James Webb Space Telescope, galaxies near the very edge of what we can see, are billions of light years away. We're talking 10, 12, 13 billion light years. Some of what we see out there left its source not long after the Big Bang itself. We are looking at baby photos of the universe. We are staring at light that is almost as old as time. And here's the thing that really gets me when I sit with this idea. We will never see these galaxies as they are right now. We literally cannot. The information about what they look like today hasn't reached us yet. It's still traveling. It won't arrive for billions of years. So, in a very real, very literal sense, everything we see in the night sky is a recording. It's not live. It's not even close to live. It's a collection of light signals from different eras, all arriving at once, creating this composite image we call the universe that is actually stitched together from millions of different moments in the past. The universe you see is not the universe that exists. It's the universe that existed. That's already a little unsettling. But here's where it actually starts to get frightening. So we've established that light takes time to travel, which means there's a limit to how far we can see. If the universe is only 13.8 billion years old, which is our current best measurement, then the furthest we could theoretically see is 13.8 billion light years, because that's how long light has had to travel since the very beginning. Makes sense, right? But here's where it gets weird. The actual observable universe, the sphere of space that we can technically detect information from, has a radius of about 46 billion light years, not 13.8, 46. Wait, how? If the universe is only 13.8 billion years old, how can we see things that are 46 billion light years away? Because space itself has been expanding this whole time. When that ancient light left its source 13.8 billion years ago, that source was much closer to us than it is now. But as the light traveled toward us, the space between us and that source was stretching. The universe was expanding. So by the time that light arrived here, the source that sent it had been carried by that expanding space to a point 46 billion light years away. It's a bit like, okay, imagine you're walking towards someone on a moving sidewalk, but the sidewalk is carrying them away from you at the same time. You can still reach them if you're fast enough, but the starting point and the ending point are very different. That sphere, 46 billion light years in radius in every direction from us, is called the observable universe. It's everything we can, in principle, receive any signal from. It's our cosmic horizon in terms of visibility, and it's enormous, unimaginably enormous. There are estimated to be around 2 trillion galaxies in the observable universe. 2 trillion. Each one of those galaxies contains hundreds of billions of stars. Each of those stars potentially has planets. The scale is so massive that the human brain genuinely cannot comprehend it. It just produces a sense of awe and a slightly hollow feeling in your chest. But here's the question I want you to hold on to. Just because we can see something, does that mean we could ever reach it? And this is where things take a very dark turn. These two things, observable and reachable, sound like they should mean the same thing, but they don't. Not even close. And the gap between them is one of the most quietly devastating facts in all of modern cosmology. Let me set this up properly. The observable universe, as we said, is about 46 billion light years in radius. It's the region from which light can reach us. The reachable universe, sometimes called the cosmic reachability horizon or the affectable universe, is much, much smaller. Much smaller. We're talking about a sphere with a radius of roughly 16 billion light years. So we can see about 46 billion light years out, but we can only physically reach, if we started right now, traveling as fast as anything can possibly travel, out to about 16 billion light years. Everything beyond 16 billion light years, already gone. Already beyond any possibility of physical contact, physical influence, physical presence, forever. And the universe we can see has a radius of 46 billion light years. You do that math, and what you find is that the vast majority of the observable universe, something like 94 to 97% of the galaxies we can see, are already in the unreachable zone, already gone, already disconnected, forever. And that number is growing. Every second, more galaxies cross that horizon. Every second, the reachable universe gets a little bit smaller relative to the observable one. The universe is visible to us, but most of it is permanently closed off. Think about that. We can see it. The light is arriving. The images are beautiful. But physically, it's as if there's a glass wall, an invisible, expanding, cosmic wall. And almost everything is on the other side of it. But why? Why is this happening? To understand that, we need to talk about the speed of light and why it isn't just fast, it's actually a kind of cosmic prison. The speed of light, about 300,000 kilometers per second, is the ultimate speed limit of the universe. Nothing with mass can reach it. Nothing can exceed it. This is one of the most tested and confirmed principles in all of physics. And at first, it seems amazing. 300,000 kilometers per second is so fast that light can travel around the entire Earth 7 times in 1 second. That's extraordinary. That seems like enough. But the universe is not impressed. At the speed of light, it would take 4 years to reach the nearest star. It would take 25,000 years to reach the center of our own galaxy. It would take 2.5 million years to reach Andromeda, our nearest galactic neighbor. So even at the maximum possible speed anything in the universe can travel, the distances are brutal, punishingly, mercilessly vast. But here's what makes it even worse. We can't actually travel at the speed of light. The speed of light is the limit for massless particles, photons, particles of light themselves. Anything with mass, any spacecraft, any probe, any human body, any possible piece of matter cannot reach that speed. The faster you try to go, the more energy you need, and as you approach light speed, the energy required approaches infinity. Literally, infinite energy. So the realistic maximum speed we'd ever be able to move anything, even in the most optimistic science fiction becomes reality future, is some fraction of light speed. Maybe, generously, in some wildly distant technological future, a tiny fraction of the speed of light. Maybe 1%. Maybe in some extraordinary scenario, 10%. But still less than light speed. Still constrained. And here's why this matters in a cosmic horror kind of way. It's not enough. Even light speed itself isn't enough to reach most of the universe, because the universe is expanding, and in many regions, it's expanding faster than light. Wait, faster than light? Didn't you just say nothing can go faster than light? Yes, and this is one of those moments where the universe reveals that it doesn't care about your intuitions. The speed of light limit applies to things moving through space. But space itself, the fabric of space-time, is not subject to that limit. Space can expand as fast as it wants to. And in the vast regions beyond our cosmic horizon, it is doing exactly that. It is expanding so fast that any light emitted from those regions toward us will never, ever reach us. The space between us and that light is growing faster than the light can cross it. Imagine you're on a treadmill, running as fast as you possibly can, and the treadmill is moving backward faster than your legs can carry you forward. You're running, you're doing everything right, but you're going backward anyway. That's what it's like for light trying to cross the cosmic horizon toward us from distant regions. It runs at the maximum possible speed, and it still goes backward. So the speed of light isn't just a fast speed limit. In the context of an expanding universe, it's a prison. The boundaries of that prison are the cosmic horizons, and they are real, they are permanent, and they are getting closer. Let's make sure we're all on the same page about what cosmic expansion actually means, because it's easy to have a picture in your head that's subtly wrong in a way that matters. When scientists say the universe is expanding, they don't mean that galaxies are flying outward through space from some central explosion point like shrapnel from a bomb. That's not what's happening. What's actually happening is that space itself, the fabric of reality, is stretching. Every point in space is moving away from every other point, not because things are moving through space, but because the space between them is growing. A useful analogy: imagine a loaf of raisin bread rising in an oven. The raisins represent galaxies. As the bread rises, the dough, space, expands between all the raisins equally. Every raisin moves away from every other raisin. There's no center, there's no edge. Every raisin would see every other raisin moving away from it. And raisins that are far apart move away from each other faster than raisins that are close together, simply because there's more dough between them to expand. This was discovered by Edwin Hubble in 1929. He noticed that galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship, known as Hubble's law, was one of the most important discoveries in the history of science, because it meant the universe had a history. It was expanding now, which meant it was smaller in the past, which meant at some point it was incredibly compressed, which eventually led us to the concept of the Big Bang. But here's the thing about the expansion that really matters for what we're discussing today. It was originally thought that the expansion might be slowing down. Gravity, the mutual attraction between all matter, should be pulling things back together over time, right? Like throwing a ball in the air, eventually gravity pulls it back down. The expectation for decades was that the universe was expanding but decelerating. Eventually, it would slow down and maybe even reverse. Then, in 1998, two independent teams of astronomers studying distant supernovae made a discovery that genuinely shocked the scientific world. The expansion wasn't slowing down, it was speeding up. The universe is not just expanding, it is accelerating. Every second, it expands faster than the second before. And that finding, which won its discoverers the Nobel Prize in Physics in 2011, is the thing that changes everything about what I've been telling you, because accelerating expansion has implications that are not just scientifically surprising, they are existentially terrifying. Okay, so let's really sit with this. The universe is expanding, and that expansion is accelerating. Here's what that means for the cosmic horizon. In a universe that's expanding but slowing down, there's some hope. As the expansion decelerates, there's at least a chance that determined, advanced civilizations could outpace the slowing expansion and eventually reach distant regions. It's hard, but maybe not impossible. But in a universe where expansion is speeding up, that hope is gone. Because the faster the universe expands, the faster distant galaxies are moving away from us, and as they accelerate, more and more of them cross the threshold, the cosmic event horizon, beyond which their light can never reach us again. Let me put a number on this that I want you to really feel. Right now, there are somewhere around 2 trillion galaxies in the observable universe. Most of them are already in the unreachable zone, beyond where we could ever travel, but many of them are still inside the observable sphere. We can still receive light from them, but as the universe keeps accelerating, those galaxies will eventually drift past even the observable horizon, not just unreachable, invisible. Their light, slowed by the expanding space, will redshift into oblivion. It will stretch until it has no energy left. It will become invisible to us, and then gone. Their photons will never arrive. Over the course of tens of billions of years, the universe is young, remember, only 13.8 billion years old, but it has a long future ahead. Galaxies that are currently visible to us will, one by one, silently disappear from the sky. Not in an explosion, not with a signal. They will simply fade. Their light will redshift into the infrared, then the microwave, then the radio, then below any frequency we can detect, and then silence. Civilizations in the far future, if any exist, will look up at a sky with far fewer galaxies than we see today. And they may have no way of knowing those other galaxies ever existed because all the evidence will have expanded beyond reach. I take the subway home most nights through this tunnel under the East River, and I sometimes think about what it would be like to watch the world just slowly contract. The tunnel stays the same size, but everything outside it gets further and further away, and you can't go back. You don't even know what you've lost because you were never able to see past the tunnel walls in the first place. That's what the far future looks like for any civilization that's still around. But here's what I haven't told you yet. What is actually causing this acceleration? Why is the universe not just expanding, but speeding up? The honest answer, the answer that every physicist on Earth will give you, is we don't know. We have a name for it. We call it dark energy. But naming something and understanding it are very different things. This is the part where I want you to really notice something. Dark energy is the most abundant thing in the universe. It makes up about 68 to 70% of the total energy content of the universe. The rest is matter, about 5% ordinary matter, the stuff we're made of, and about 27% dark matter, which is itself another huge mystery. But dark energy, this thing that is driving the accelerating expansion, this thing that is slowly sealing off the cosmos from itself, this accounts for the majority of everything, and we have almost no idea what it is. We're not being modest here. This isn't, we know roughly what it is, but haven't worked out the details. Scientists genuinely do not know the nature of dark energy. They do not know where it comes from. They do not know why it has the strength it does. They do not know if it changes over time. They do not know if it is truly a constant or if it might one day switch off or intensify. One leading hypothesis is that dark energy is the cosmological constant, a property of space itself. Einstein actually introduced the cosmological constant, then famously abandoned it, calling it his greatest blunder. Ironically, it turned out something like it was needed after all. The idea is that empty space has an inherent energy, a quantum property of the vacuum that acts like an outward pressure, pushing space apart. And the more space there is, the more of this energy exists, which is why the expansion accelerates. More space means more dark energy, means more expansion, means more space. It's a runaway process. Other hypotheses include something called quintessence, a dynamic energy field that varies over time and space, or phantom energy, which would be even weirder and potentially lead to a big rip scenario where the expansion eventually tears apart galaxies, stars, planets, atoms, and space-time itself. Or there are modifications to Einstein's general relativity that might explain the acceleration without invoking a mysterious energy at all. We don't know which of these is right. We might not even have the right framework yet. I was reading a paper once, well, trying to read it. It was pretty heavy going, And there was this line buried in the middle of it that I've thought about a lot since. The author said something to the effect of, "The cosmological constant problem is arguably the deepest unsolved problem in theoretical physics." The cosmological constant problem, briefly, is this. When physicists calculate what the vacuum energy of space should be based on quantum field theory, they get a number that is vastly, unfathomably larger than the dark energy we actually measure. We're talking about a discrepancy of something like 120 orders of magnitude. That's a 1 followed by 120 zeros. That's not a small error. That's a catastrophic mismatch between our best theories of the very small, quantum mechanics, and our best theories of the very large, general relativity. Something is deeply wrong with our understanding, and whatever is actually going on at that level of physics, that's the thing that's also driving galaxies apart and sealing off the cosmos. We're living with a universe whose dominant feature we don't understand, and that feature is actively taking the universe away from us. Let's talk about what that looks like in practice, how individual galaxies are disconnecting from us one by one. Let's get specific, because the abstract can feel comfortable. The specific is where it really hits. Right now, every galaxy that's more than about 16 billion light years away is already in the unreachable zone. A photon leaving those galaxies today and heading toward us will never arrive. The expanding space will carry it backward, not dramatically, not in an explosion, just slowly, relentlessly, until it is stretched to oblivion. But what about galaxies that are closer? What about the ones that are technically reachable, at least in principle? Here's the unsettling part. That zone is shrinking. Every year, the cosmic event horizon, the boundary of the reachable universe, contracts. Galaxies that are near the edge of the reachable zone today will be just outside it in the future. As expansion accelerates, the threshold creeps inward. There's a specific number that defines this: the Hubble distance. Right now, the Hubble distance, the distance at which the recession speed of a galaxy equals the speed of light, is about 14 billion light years. Galaxies beyond this distance are receding from us faster than light. Their light can still reach us because that light was already in transit from when the galaxy was closer, but any signal we sent today would never reach them. And as the universe expands and accelerates, this Hubble distance stays roughly constant while the universe grows. So, more and more galaxies tip over the edge. Let me put it in personal terms, even though it sounds absurd. Imagine you're at a party. Okay, a much better party than any party I've been to in New York, which usually involves cramped apartments and not enough chairs. But imagine a party where you're trying to have a conversation with someone across the room. They keep walking backward, slowly at first. You walk toward them. They drift back. Eventually, they're so far away that your voice can't cross the distance, but you can still see them. They look fine. They're still at the party, technically, but communication, any possibility of it, is gone. Now imagine you can see hundreds of billions of those people, and almost all of them have already drifted too far to hear you, and you didn't even notice it happening. That's what's occurring with galaxies right now, in real time, silently. Most of what we see in the sky has already drifted past the point where any signal we send could ever reach it. And this isn't a future problem. This is the current state of the universe. We were born into a cosmos where most of it was already beyond our reach. And it's been this way for billions of years. The question that haunts me, the one I keep coming back to, is, can something be visible to us but already permanently unreachable? That sounds paradoxical. Let me explain exactly why it isn't. Yes, absolutely yes. And this is one of the most counterintuitive things about cosmology. We tend to conflate visibility with accessibility. If I can see something, surely I could walk to it eventually, right? If I can see a light at the end of a very long hallway, I can, in principle, reach it if I just walk far enough. That intuition breaks down completely when space itself is expanding. Think of it this way. Right now, as I'm speaking to you, there are galaxies out there, billions of them, from which light is reaching us. We can see them, we can photograph them, we can analyze their spectra, measure their distances, understand what kinds of stars they contain. The information is arriving, but if we launched a spacecraft today, moving at the speed of light, the maximum possible speed, toward one of those visible galaxies that is beyond the Hubble sphere, that spacecraft would never arrive. Ever. The space between us and that galaxy is expanding faster than the spacecraft can move. Every second, the destination moves further away, faster than the ship can close the gap. It's like running toward the horizon. You can see it clearly, it doesn't disappear, but you can never reach it because it recedes as you approach. The light from those galaxies is still reaching us because it was launched before those galaxies crossed the event horizon. The light was already in transit, already committed to crossing the space. But a new signal, sent today, too late. I think about this sometimes when I'm on my roof at night. I live on the 6th floor of a walk-up in Brooklyn, and sometimes on clear nights in summer, I'll go up there just to breathe and look out. You can see some stars from there, not many, but some. And I think every single photon hitting my eyes right now is an old message. It was sent before I was born, before my parents were born, before my country existed, before the Egyptian pyramids. Some of those messages were sent before the earth even formed, and some of those messages were sent from places we can see but could never reach. Even if every human who ever lived had devoted all their energy and all their technology to the project. Visible, but gone. The word gone here needs a little clarification though, because I want to be precise. Those galaxies still exist, almost certainly. They're out there. Stars are forming in them. Maybe planets. Maybe life. None of that has stopped happening just because we can't reach them. From their perspective, if there's any perspective to speak of there, they are not gone at all. But from our perspective, from the perspective of what we can interact with, travel to, communicate with, be affected by, gone, forever, as completely and permanently as if they had never existed, which raises the question, can something be real if we can never in any way interact with it? That's getting into philosophy more than physics. But I'll say this, the physics is clear. Those galaxies are real, and they are gone. Both things are true at the same time. And when you start adding up how many galaxies are in that visible but gone category, you get to the number that changes everything. Let's put the numbers together. The observable universe, roughly 46 billion light-years in radius, approximately 2 trillion galaxies. The reachable universe, roughly 16 billion light-years in radius, a significantly smaller volume. Volume scales with the cube of the radius. So the ratio of volumes is roughly 16/46 cubed, which is about 0.042, about 4%. That means only about 4% of the observable universe by volume is even theoretically reachable. The other 96% is already permanently, cosmically off limits. 94 to 97% of all the galaxies we can see, those 2 trillion galaxies, are already beyond any possible physical reach. We cannot send a probe there. We cannot send a message there. We cannot go there. If they contain life, we can never meet it. If they contain wonders, we can never experience them. They are visible and they are gone. And remember, the reachable zone is shrinking. It will continue to shrink for as long as dark energy continues to drive the expansion. So that 4% will become 3%, then 2%, then less. More galaxies will tip over the edge every year. More will become unreachable at some point far in the future, but a point that exists on the timeline. Even our neighboring galaxies will start to become unreachable. The Milky Way and Andromeda are actually on a collision course, which will eventually merge into a single large galaxy. That merged galaxy and a few of its closest companions are gravitationally bound. The expansion won't separate them. But everything else, everything beyond our local group of galaxies, already unreachable, already gone. The local group, our little neighborhood of maybe 50 to 80 galaxies, will eventually be our only visible universe, the only galaxies that remain within sight. The rest will have faded into the dark. One author I read described this with a phrase I haven't been able to forget. He called it the end of cosmology, not because the universe ends, but because future civilizations, if any survive that long, will lose the ability to even study most of it. The evidence will be gone, the light will have faded, the records will have been destroyed not by any catastrophe, but simply by expansion. I think about this sometimes when I throw out old photographs, not digital ones, actual printed photos from disposable cameras when I was a kid. Once they're gone, that information is gone. The moment they captured can never be reconstructed. And it occurred to me, that's what the universe is doing with itself. It is slowly throwing away its own photographs, letting them drift past the horizon, past the point where they can ever be seen again. Most of the universe is already in that garbage bag, and nobody knows why. Not really. I want to spend some time here because I think the honest picture of what we do and don't know is more interesting and more unsettling than any oversimplified version. We know the universe is expanding. The evidence for that is overwhelming and comes from multiple independent lines of observation. We know the expansion is accelerating. The evidence for that, discovered in 1998, has been confirmed repeatedly and was deemed reliable enough to warrant a Nobel Prize. We know that dark energy is the leading explanation, the placeholder name for whatever is causing this acceleration. When you put dark energy into our cosmological models, things fit beautifully. The models describe the universe we observe with remarkable precision, but knowing that dark energy works in our models is different from knowing what dark energy actually is. And here's where it gets philosophically interesting. There's a principle in physics. It's not a law, more of a meta-principle, called the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic, meaning it's roughly the same in all directions and looks roughly the same from all locations. No special places, no special directions. This has generally worked well, and it's built into almost all our cosmological models. But recent observations, and this is genuine current scientific debate, not fringe stuff, have started to hint at possible tensions in this picture. There's something called the Hubble tension. When you measure the expansion rate of the universe using different methods, you get slightly different numbers. This disagreement has been growing over the past decade. It's not huge, but it's larger than the measurement uncertainties should allow. Something might be slightly wrong with our models. There's also some evidence, contested but real, of what might be large-scale structures or flows in the universe that challenge the uniformity assumption. These are things like the Great Attractor, a massive concentration of mass toward which our galaxy seems to be falling, or the cold spot in the cosmic microwave background that some researchers have speculated could be the imprint of another universe from before the Big Bang. Most of this is tentative. Science is cautious, and rightly so. But the point is, we might not even have the right model yet. The cosmological model we use, the lambda CDM model, is successful, but it has a dark energy term we can't explain and a dark matter component we can't directly detect. Two of the three main components of our universe are complete mysteries. We live in a universe we can measure but not understand. We know what it does, but not what it is, and what it's doing right now, quietly, while you watch this video, is putting more and more of itself permanently beyond our reach. I find it genuinely humbling and genuinely frightening in equal measure. Not the kind of frightening that makes you want to run, the kind of frightening that makes you very, very still. Let me paint you a picture of the future, not the near future, not even the future of human civilization, which has its own terrifying uncertainties. I mean the deep future, the billion-year future, the trillion-year future. Right now, on a very dark night, far from city lights, you can see with your naked eye maybe a few thousand stars. With a decent telescope, you can see galaxies, Andromeda, the Triangulum Galaxy, various members of our local group. With a really powerful telescope, you can see billions of light years out. What will the night sky look like in a trillion years? First, let's deal with the stars. Our sun will be gone in about 5 billion years. It will exhaust its hydrogen fuel and expand into a red giant, eventually collapsing into a white dwarf. Most sun-like stars have similar lifespans. The longest-lived stars, tiny red dwarfs, can burn for 10 trillion years. So, there will still be some stars for a very long time. But the galaxies, the other galaxies, will begin to disappear. Our local group, the Milky Way, Andromeda, and our small collection of dwarf galaxies will eventually merge over billions of years into a single enormous elliptical galaxy. Some people call this future merged galaxy Milkomeda or Andromilky, which are genuinely funny names for something genuinely sobering. Beyond that merged remnant, all the other galaxies, the ones currently in clusters like the Virgo cluster, the Coma cluster, all the vast cosmic web of galaxy filaments and voids we see today, those will recede past the cosmic horizon. They will redshift into darkness. Their light will fade below any detectability. A civilization living in Milkomeda in, say, 100 billion years will look up at a night sky and see their own galaxy, stars within it, and then nothing, complete darkness beyond. No other galaxies, no hint that the universe extends beyond their own island of stars. They will have no way to know that the universe was once full of trillions of galaxies, brilliant and varied, spread across 46 billion light years. All the evidence will have drifted away. All the light will have stretched into the dark. The cosmic microwave background, that faint afterglow of the Big Bang that we can detect as a faint radio signal in every direction, will have redshifted to impossibly long wavelengths, below any detectable frequency. Gone. If those future beings try to figure out whether the universe had a beginning, they'll find no evidence. They'll live in what looks like a static island of stars surrounded by eternal dark, and they might conclude the universe is just this, their galaxy, forever. They won't be wrong exactly. It's just that they'll have arrived so late that the universe will have already hidden its own history from them. Now, here's the question that this raises for us. We live 13.8 billion years after the Big Bang. The universe still has trillions of years ahead of it. By some measures, we're at a relatively early point in the universe's story. But for the purposes of observing the cosmos in its full variety and richness, for the purposes of being able to look out and see the universe as it actually is, did we arrive too late? This is one of those questions that hits differently the more you think about it. In some ways, we got incredibly lucky. We exist at a time when the universe is still rich with visible galaxies. We exist at a time when the cosmic microwave background is detectable and tells us about the birth of the cosmos. We exist at a time when the universe is still relatively structured. Stars are forming, galaxies are interacting, there's tremendous variety. If we had arrived, say, 1 trillion years later, almost none of that would be accessible to us. We'd be marooned in a single galaxy, surrounded by darkness, with no way to know the universe we couldn't see. So, in that sense, we're early, we're lucky. But here's the twist. The question isn't just, are we early enough to see the universe? We are. We can see it. It's spectacular. The question is, are we early enough to reach it? And the answer to that is almost certainly no. The window for reaching most of the universe has been closing since the beginning. Even the moment matter first formed, after the Big Bang, the expansion was already carrying most of the volume of the universe beyond any traversable distance. The window to reach most of the cosmos opened and closed before the first stars ever ignited. And this isn't just about physical travel. Even with information, with light, with signals, the window to communicate with most of the universe is already closed. Any message we send today to a galaxy 20 billion light years away will never arrive. We're already past the point of no return. If there were beings in the earliest moments of the universe, beings in some hypothetical early cosmic civilization that arose around the first stars, perhaps 200 million years after the Big Bang, they would have had access to a slightly less expanded universe. The window would have been slightly wider, but only slightly, because even then, most of the universe was already beyond the reachable horizon. There was never a golden age of cosmic accessibility. There was never a time when all of the universe was open for exploration. The expansion was always happening. The horizons were always there. In a way, the universe has been closing itself off from the very beginning. Every moment we have existed, more of it has moved beyond reach, and we never had the chance to catch what was lost because we weren't here yet. I don't know about you, but that gives me a very specific feeling, a quiet, heavy feeling. Like arriving at a party to find that most of the people you came to meet have already left, and they left hours ago, and there was nothing you could have done because you were physically incapable of getting there earlier. The universe had this brief, brilliant window of accessibility, cosmically brief, and we arrived right in the middle of it. Not early enough to use it, but late enough to see what we're missing. Which brings me to something I've been building toward this whole time. Something that, once you connect it, feels both obvious and devastating. The Fermi paradox. If you haven't heard of it, here it is in brief. The universe is enormous. It's 13.8 billion years old. There are 2 trillion galaxies, each containing hundreds of billions of stars. Many of those stars have planets. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, are common throughout the cosmos. Life on Earth emerged relatively quickly after conditions became suitable, so statistically, it seems almost inevitable that life should have emerged elsewhere, possibly many times over, possibly billions of years before life emerged on Earth. And if intelligent life arises elsewhere with any frequency, if even a tiny fraction of life-bearing planets develops technological civilizations, then over billions of years, some of those civilizations should have had time to expand across their galaxies, to build megastructures, to send signals, to do something that we could detect, but we detect nothing. The universe is silent. No signals, no visitors, no megastructures, no obvious traces of any other technological civilization anywhere. Where is everybody? That's the Fermi paradox. Enrico Fermi supposedly asked it casually over lunch. The question has haunted scientists ever since. There are many proposed explanations. Life is rarer than we think. Civilizations destroy themselves. The distances are too vast. We're not listening properly. They're hiding. We're in a zoo or a simulation. The list goes on. But here's the explanation I want to add to that list. Not as a replacement for the others, but as an additional layer that most popular discussions of the Fermi paradox skip right past. Maybe the universe isn't empty. Maybe it's separated. Maybe there are civilizations out there, perhaps many of them, some of them ancient, some of them brilliant beyond anything we can conceive, and they are just on the other side of the horizon, not hidden, not silent by choice, simply unreachable, simply disconnected by the same expanding space that is pushing everything apart from everything else. Think about it. If civilizations exist in galaxies beyond our cosmic event horizon, we will never receive a signal from them. They can broadcast all they want. Their signals, no matter how powerful, will never cross the expanding void. We are causally disconnected from them, not just far apart, but in different cosmic neighborhoods with no bridge between them. And they're in the same situation. Even if they look out at their universe, even if they have their own Fermi paradox. Where is everybody? They cannot see us either. We are on the other side of their horizon. The universe may be teeming with life, teeming with civilizations, teeming with activity, and we would never know. Not because they're hiding, not because we're looking wrong, but because the space between us has expanded past the point where any connection is possible. This is a version of the Fermi paradox answer that doesn't require any catastrophe, any filter, any inherent rarity of life. It only requires the universe to be old enough and to have expanded fast enough, which it is, and it has. I find this particular answer to the Fermi paradox uniquely unsettling because it doesn't require anyone to fail. No one has to die out. No one has to be rare. Everyone just has to be separated. And the expanding universe does that without asking. Civilizations could be calling out right now. Right now, the signals are traveling, and they will be traveling forever, stretching, fading, and never arriving. I want to take a moment to address the hope that technology might eventually solve this, because that's a natural response. When I tell people about the cosmic event horizon, about how 94+% of the observable universe is already unreachable, one of the first reactions is, but what about future technology? What about warp drives? What about wormholes? Surely sufficiently advanced beings could find a way. Let me engage with this seriously, because it deserves a serious answer. First, warp drives. The concept, specifically the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is based on real physics. General relativity does not, in principle, forbid distorting space-time in a way that would allow a bubble to move faster than light relative to distant observers. The ship inside the bubble wouldn't be moving faster than light. It's sitting still while the space itself moves. Think of it like standing on a conveyor belt. But there are problems, enormous problems. The energy required to create such a warp bubble, based on the best current calculations, is literally astronomical. Originally estimated at equivalent to the mass energy of Jupiter, and more recent calculations haven't made it more feasible. There are also serious theoretical problems involving negative energy, exotic matter, and causality that may make the Alcubierre drive fundamentally impossible rather than just technologically difficult. But let's grant for the sake of argument that some future civilization found a way to move through space arbitrarily fast. Could they reach galaxies beyond the cosmic event horizon? No, and here's why. The cosmic event horizon isn't about speed, it's about causality. To reach a galaxy beyond the event horizon, you would need to travel through regions of space that are themselves expanding faster than light. Even if your ship could somehow move faster than light through local space, the global structure of the expanding universe would defeat it. You'd be running on an ever-accelerating treadmill. The event horizon is not a wall in space, it's a feature of the geometry of space-time, and getting past it would require not just fast travel, but a fundamental alteration of the large-scale structure of the universe, which would require controlling dark energy itself. Wormholes? These are theoretical tunnels through space-time, shortcuts between distant points. General relativity does allow solutions to its equations that look like wormholes, but traversable wormholes, ones you could actually use as a transport route, require exotic matter with negative energy density, which may not exist, and even if they do, connecting a wormhole to a region beyond the event horizon would require the mouth of the wormhole to have been placed there before it crossed the horizon, which requires foresight on a cosmic scale and a level of engineering that borders on magic. Could there be physics we haven't discovered yet that changes this picture? In principle, yes. We don't know everything. Our models might be wrong or incomplete, but the event horizon emerges from the most fundamental principles of general relativity and the thermodynamics of expanding space-times. Any future physics that invalidates it would have to be so radical as to completely overturn our understanding of space, time, causality, and information. The honest answer is, the cosmic event horizon looks like a genuine, permanent boundary. Not a technological challenge, a fundamental one. Even a civilization that has mastered fusion, that has colonized its entire galaxy, that has been around for 1 billion years, cannot cross it. The universe's own structure prevents it. This is one of the few things in the universe that doesn't yield to intelligence or effort. The horizon is the horizon, and it's moving inward. I've been building to this. Let me just say it plainly. The universe contains, almost certainly, a vast wealth of existence. Stars, planets, perhaps life, perhaps intelligence, perhaps beauty and complexity and wonder that we can barely imagine. The scale of what's out there is almost certainly greater than anything our civilization has ever contemplated. And almost all of it is already beyond reach, already separated from us, already in the dark, from our perspective. This is not a disaster that happened. It's not a catastrophe we can fix. It's just the nature of the universe we live in. The expanding cosmos, driven by dark energy that we don't understand, has been placing limits on cosmic accessibility from the very beginning. And those limits are permanent and growing. The greatest tragedy of the universe, if we want to call it that, is not that it's empty. It may not be empty at all. The tragedy is that it is so full and so thoroughly beyond reach, and we can do nothing about it. When I think about this, really sit with it, I feel something I don't have a precise word for. It's a mixture of awe and grief and a strange kind of vertigo, like standing on the edge of something enormous and real, knowing that looking is all you can do. I had a professor in college, not in cosmology. I was an English major originally. I changed later. But I had a professor who used to say that the truly tragic things in life aren't the things that go wrong. The truly tragic things are the things that can never go right. Not because of failure, just because of the structure of reality. I think about that a lot when I think about the cosmic horizon. It's not that we tried to reach those galaxies and failed. It's that the reaching was never possible. The structure of reality itself, the geometry of space-time, the behavior of dark energy, the speed of light, built these walls, and they were built before we existed to notice them. And here's the dimension of this that I find most quietly devastating. Those galaxies we can see but cannot reach, they contain everything. They contain entire histories, entire cosmic evolutions. If there's life out there, and statistically, the chances feel impossibly slim that we are unique. There are whole civilizations, whole stories, whole minds, having experiences and reaching conclusions and making things in those galaxies we can never touch. And all of that, all of it, is moving away from us, faster every second, forever. The universe is not empty, it's full, but its fullness is sealed off from us. Its wealth is behind glass we can never break. That's the tragedy. And here's the final twist on it. We're not even sure this is the tragedy's final form. I want to end, or rather near the end, with an idea that I think is the most unsettling framing of everything we've discussed. What if we're not approaching the closing of the cosmic door? What if it already happened? Here's what I mean. We've talked about the event horizon, the boundary of the reachable universe. We've talked about how 94+% of the observable universe is already beyond it. We've talked about how this zone is shrinking. But there's a more radical way to think about this. The moment the accelerating expansion became dominant, the moment dark energy took over from the gravity-dominated universe, the die was essentially cast. That happened roughly 5 to 6 billion years ago, around the time our solar system was forming. Before dark energy became dominant, the universe was decelerating. Expansion existed, but gravity was the dominant force. Things were slowing down. There was at least a theoretical future in which the expansion reversed, in which the universe collapsed back on itself, in which the distances between things shrank. Then, dark energy became dominant. The deceleration flipped to acceleration. The fate of the universe switched from potential collapse to eternal expansion. The cosmic horizons, which had been in some sense closing in as expansion slowed, reversed direction and began to pull away. At that moment, 5 or 6 billion years ago, the question of cosmic reachability was answered. Not for us specifically, but in principle. The universe committed itself to a path that leads to ever-increasing disconnection between its parts. Every part of the universe is, from that moment, on a trajectory toward isolation. We inherited that committed universe. We were born into it. We never had a choice. And the thing is, we're not even the most isolated part. Right now, we're in a relatively cozy position. We have our local group. We have the visible universe. We have 13.8 billion years of cosmic history encoded in the light reaching us every night. Future civilizations will have less, much less. The universe is not being taken from us suddenly. It's being taken from us slowly, quietly, over billions of years, and it started before we arrived. In a way, this is the ultimate long game. The universe's own expansion has been working against the possibility of cosmic community from the very beginning. And by the time any civilization smart enough to notice this problem existed, it was already, mostly, too late. I was outside last week, late night, coming home from a friend's place in the West Village, and I stopped on the corner for a minute. It was cold and clear, and you could see a couple of stars between the buildings. Orion's belt, I think. 3 stars in a row. And I thought, those stars are inside the Milky Way, inside our galaxy, maybe 1,000 light years away, some of them. Well, within even the most conservative reachable zone, and I felt this strange dual feeling. These tiny points of light are within reach, cosmically speaking, and yet even these are impossibly far for us right now with our current technology, and beyond them, stretching 46 billion light years in every direction, is a universe of 2 trillion galaxies, and most of them are already gone. Not dark, not destroyed, just sealed off, behind the expanding horizon, on the other side of a wall that will never come down. And I just stood there in the cold for a while, and then I walked home. I want to return to the Fermi paradox one more time because there's a layer to it that I glossed over earlier and I think deserves more attention. There are many proposed filters in the discussion of the Fermi paradox. Great filters that might prevent civilizations from becoming spacefaring or from lasting long enough to be detected. Things like the emergence of multicellular life, maybe that's rare. The development of intelligence, maybe that's rare. The development of technology without self-destruction? Maybe that's rare? The cosmic expansion problem adds a different kind of filter. Not a filter that kills civilizations, a filter that separates them. Even if the universe is absolutely teeming with life, even if the emergence of life and intelligence is common, maybe inevitable given sufficient time, the expanding universe ensures that most of that life is, and has always been, cosmically isolated from most other life. Different galaxies are already separated by distances too vast to communicate across, even in the absence of expansion. With expansion, even the possibility of eventual communication, even with the slowest, most patient message-in-a-bottle style contact over millions of years, becomes impossible for most of the universe. If a civilization in a galaxy 20 billion light-years away sent a signal toward us the moment their planet formed, if they had been transmitting for 4 billion years, that signal would never arrive. The expanding universe would stretch it out, redshift it to nothing, lose it in the cosmic dark. We could be surrounded, in the cosmological sense, by voices, billions of them, and we would hear nothing, not because space is vast, but because the space is actively working against communication. The expanding universe is the best ever excuse for silence. And if that's true, if the universe is full but separated, then the silence we experience when we look for signals isn't evidence of emptiness. It's evidence of expansion. It's evidence of dark energy. It's evidence of the cosmic horizon. The universe is not quiet because it's empty. It might be quiet because it's sealed. And we're every civilization, everywhere, sealed in our own little bubble of reachable space, surrounded by an ocean of visible but untouchable existence. Doesn't that reframe everything? The loneliness we feel when we contemplate the Fermi paradox. Where is everybody? Isn't the loneliness of an empty universe. It might be the loneliness of a full universe where everyone is separated by walls they can't break, where everyone is looking up at their sky, seeing billions of galaxies and hearing nothing, where everyone is sending signals that nobody can receive, where everyone is, in the deepest cosmic sense, alone. Not because they're alone, but because alone is what the universe makes you when space expands faster than signals can travel. I don't have a word for that kind of loneliness. I don't think any human language has a word for it, because it's a loneliness we've only recently become smart enough to understand. All right, I want to bring this back to Earth. Literally, everything I've talked about is on cosmological scales. Billions of light years, billions of years. These are not things that affect your Tuesday morning, but I think there's something genuinely valuable in sitting with these ideas. Not because they're frightening, though they are, but because they reframe things in a way that's clarifying. We are, in the context of the universe, extraordinarily local. Everything that has ever happened to humanity, every war and every discovery and every love story and every piece of music and every moment of grief and every scientific breakthrough, all of it happened in a tiny region of a single galaxy, in a universe of 2 trillion galaxies. Most of those galaxies already beyond our reach. From the cosmic perspective, we are so small as to be almost undetectable. And yet, and this is the thing I always come back to, we are the only part of the universe that we know for certain is aware of the rest of it. The galaxies beyond the horizon aren't contemplating their own isolation. They don't know they're beyond our reach. They're not experiencing anything about this situation, as far as we know. They're just there, or not there, or whatever they are. But we are here, and we know about them, and we can feel the weight of what it means that they're unreachable. That's kind of remarkable, actually. The universe is enormous and mostly sealed off from itself, and in one tiny corner of it, there's this weird collection of conscious creatures who figured out the mathematics of the horizon, who can measure the rate at which the universe is sealing itself off, who can calculate, in detail, exactly how much they can never have. That's us, right now, on this video, at this moment. And I think that's worth something. I'm not sure what exactly, but it doesn't feel like nothing. The poet Rilke wrote, and I know this is a strange pivot from cosmology, but bear with me. He wrote something to the effect that we should live the questions rather than seeking the answers too quickly. Because the questions themselves are where the life is. The question of the cosmic horizon. Why is the universe doing this? What is dark energy? Are we alone because the universe is empty or because the universe is sealed? These are live questions. They don't have answers yet, and maybe they won't for a very long time, but they're worth asking. They're worth sitting with. They change how you see things. I know they've changed how I see things. One thing I want to be clear about before we wrap up, this is not a closed story. The science of dark energy and the expanding universe is one of the most active areas of research in modern physics and cosmology. There are major telescope projects: Euclid, the Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, dedicated in part to mapping the expansion of the universe with unprecedented precision. The goal is to understand dark energy better, whether it's constant, whether it varies, whether there are hints of its true nature hiding in the data. The Hubble tension I mentioned earlier, the discrepancy between different measurements of the expansion rate, is being taken increasingly seriously. Some physicists think it might point to new physics, something beyond the standard cosmological model, something that, if confirmed, could rewrite our understanding of the universe's history and fate. There's even a small group of researchers who think dark energy might eventually weaken. If the cosmological constant is not actually constant, if dark energy decreases over time, the universe might shift from acceleration back to deceleration. The event horizon might actually retreat, becoming more expansive rather than less. Galaxies that are currently just beyond reach might come back within reach. This is speculative, but it's not crazy. It's based on real theoretical frameworks, and conversely, and this is the really scary version, dark energy might strengthen. There are models in which dark energy increases over time, leading eventually to the Big Rip scenario I mentioned earlier, a universe in which the expansion rate becomes so extreme that it tears apart not just the cosmic web, not just galaxies, not just solar systems and planets, but eventually atoms and space-time itself. An apocalypse, not of fire or cold, but of pure unbounded expansion. We don't know which of these futures we're in. The data we currently have is most consistent with dark energy being a constant, the cosmological constant, but the uncertainties are large enough to accommodate other possibilities. And this is genuinely terrifying in a specific way. We don't know what the universe is going to do, not just in the far future. We don't even fully know what it's doing right now. We are inside a system we cannot step outside of. We are trying to understand the universe using only the information the universe has allowed to reach us. And as the cosmic horizon contracts, that information is getting smaller, not larger. We are doing science under conditions of increasing cosmic isolation. And at some point, again, far in the future, that isolation will become so complete that science itself becomes impossible for any future beings because the universe will have hidden its own evidence. It's like being a detective who can only investigate a crime scene that's being cleaned up as you work. And the cleaning crew gets faster every year, and eventually you'll have nothing left to examine. I want to stop for a moment. We've covered a lot of ground. Expanding space, dark energy, observable versus reachable, event horizons, the Fermi paradox, the deep future, the question of whether we arrive too late. It's a lot to carry. Let me just say this. I don't think this knowledge should make you despair. I really don't. I know it sounds bleak when I lay it out like this, and it is, in certain ways. The cosmic isolation is real. The unreachable galaxies are real. The accelerating expansion is real. But here's the other side. We are alive now, in this universe, at this moment, and the universe, even our small, local, reachable corner of it, is extraordinary. The Milky Way alone contains hundreds of billions of stars. Our solar system alone contains wonders we've barely begun to understand. The oceans, the biosphere, the fact that matter assembled itself into beings capable of wondering about their own smallness. The unreachable parts of the universe are unreachable, but the reachable parts, even the tiny fraction that's within our cosmic neighborhood, are more than any civilization could exhaust in any timescale we can meaningfully imagine. And the knowledge that most of the universe is already sealed off, I think it makes what's here more precious, not less. We didn't get all of it. We never had all of it. But what we have, this galaxy, this solar system, this planet, this moment, isn't diminished by the existence of horizons we can't cross. If anything, it's illuminated by them. There's something I sometimes do when the city gets to me, when New York feels too loud, too pressured, too full of everyone's urgency. I'll go to the roof and just be still for a minute, not thinking about anything specific, just looking up. And the stars, when I can see them, don't feel like things that are leaving. They feel like things that are here, right now. Just a few of them, fighting through the light pollution, but here. That feels like enough in those moments, not because I've resolved anything, not because the cosmic questions are answered, just because presence is its own thing. The universe is sealing itself off, and we are here, right now, for this window. I think that's worth noticing. Let me give you the full picture one final time. The universe is 13.8 billion years old. It contains roughly 2 trillion galaxies spread across a sphere of about 46 billion light-years in every direction from us. Of those 2 trillion galaxies, roughly 94 to 97% are already beyond the cosmic event horizon, beyond any possible physical reach, regardless of our technology, regardless of our cleverness, regardless of how long we wait. The expansion of the universe is accelerating, driven by dark energy, a phenomenon that comprises about 68% of the total energy content of the cosmos, which we do not understand and cannot currently explain. Every second, more galaxies tip over the edge of the event horizon and become permanently disconnected from us. Every second, the reachable universe shrinks. Every second, the universe seals off more of itself. Tens of billions of years in the future, the only galaxies visible to any civilization will be those within the local group, our own gravitationally bound neighborhood. The rest will have faded to black. The evidence of the cosmos's full richness will be gone. The cosmic microwave background will be gone. The data that tells the story of the universe will have drifted past the horizon, and there was never a time when we could have prevented this. The expansion has been happening since the beginning. The horizons were always there. We arrived into a universe already mostly sealed off from itself. Maybe there is life out there, in those 96% of galaxies we can never reach. Maybe there are civilizations. Maybe there are signals being sent right now that will never arrive. Maybe in a galaxy 30 billion light-years away, there are beings looking at their own version of this sky, asking their own version of this question, and arriving at their own version of this answer. And we will never know. And they will never know about us. The universe is not empty. It is full. It is sealed. And it is leaving. What we see is not a live view of the cosmos. It's an old recording, arriving late, from places we can never visit. We are surrounded by light from the past, from sources already beyond reach, from a universe that has already, in large part, closed itself off from us. The night sky is beautiful, and it is a photograph of something mostly gone. So, I want to leave you with a question, and I mean this genuinely. I think about it myself, and I don't have a definitive answer. Do you think humanity arrived too late to the universe? We're here at a moment when the cosmos is still visible in its full richness. 2 trillion galaxies, the microwave background, the full record of cosmic history encoded in light that's still arriving. We can see it all. We can measure it all. We have this extraordinary, unrepeatable window, but we can't reach most of it. And that window, the observational window, the full cosmic picture, will eventually close too. So, too late to participate in the universe? Probably yes, mostly. Too late to understand it? Maybe not yet, but the clock is running. I think about what it would mean to take that seriously, to understand that this moment, right now, is a kind of cosmic privilege, that future beings, if they exist, will have far less to work with, that the richness of what we can observe is not permanent, that the universe is not going to wait. I don't know what to do with that. Practically speaking, I don't think it means we should panic. I think it means we should pay attention to the science, to the questions, to the fact that we are, right now, in the middle of figuring out what the universe is, while we still have enough of it left to figure out. If any of this hit you the way it's been hitting me, if you found yourself staring at the ceiling at some point during this video, thinking, wait, hold on, that actually means... I'd love to know what you're thinking. Drop it in the comments. Genuinely, I read them. And if you want to go deeper on any of these topics, dark energy, the observable universe, the Fermi paradox, the fate of the cosmos, subscribe and stick around. We're going to keep pulling on these threads. The universe may be closing off from us, but we've still got time to look. Thanks for being here.